So we will discuss the problem of the day of GFG. So what we have been asked is that we have been given an array ARR of size of containing n integers including 0, and our task is to find the smallest positive number missing from the array. And we know that the smallest positive number starts from 1, 2, 3 and so on. So in the array we have to tell the smallest positive number which is not present in the array. Okay. So for example, let's see this example. You can see 1 is present here, 2 is present here, 3 is present here, 4 is present here, and 5 is present here. So answer would be 6, because 6 is this first smallest positive number which is missing in the array. Okay. And now if we consider the second example, so obviously we will neglect negative number because that can't be our answer, and we have to ignore the negative number and also 0. Okay, so let's see just the positive number 1 and 3. So you can see 1 is present but 2 is not present, that's why 2 is our answer. And also one thing you should observe, that it is not necessary that the array is sorted, just in the just as an example 1. Okay, so how to approach this problem? So in the interview, first you should tell the brute force approach. Okay, so what will be the force approach? Obviously you would start from the smallest positive number, which I have told it is 1, which we know that it is 1. So we will start from 1 to n. Why 1 to n only? Because we know that even if all the positive numbers starting from 1 to n was there, then obviously it would have been present, uh, but if it is greater than n, obviously it can't be accommodated in the array. Okay, what I mean is that suppose n is 5, so 1, 2, 3, 4, 5. So you can see that uh, and if suppose 5 is not present, it is 6, then obviously we would if we would check up till n, then we would have encountered 5 that it is not present in the array, so we would have written 5 as our answer. That's why I had told you to check until n. So what I mean is that if a of ai is greater than n, so we would have to neglect it. Okay, and one thing, if it is less than equals to 0, then also we have to continue. So let's just code the brute force, although it will not pass because n is quite high, it means 10 to the power 6. So for int I is equals to 1, I less than equals to n, I plus plus. For int j is equals to 0, j less than n, j plus plus. If ARR of j is less than equals to 0, or ARR of j is greater than n, just we have to continue. Else, if we encounter ARR of j equals to I, in that case we would have to return, we would have to continue, means let's just declare a bool variable, bool found is equals to false. Okay, so in this case we would just break found is equals to true, break. Okay, so suppose if it is found, if found, so we would return I as our answer. And suppose after coming out of this nothing has been returned, so surely it would be n plus 1. Why? Because if all the elements why the answer is not returned? It means that all the elements were, sorry, all the elements were present in the, all the elements from all the positive numbers from 1 to n was present in the array. That's why it was not returned. But if we have come out of this loop, this means that all the elements were present, so the next element would not have been present, just like in this case 1 2 3 4 5 all were present from 1 to n, so we returned the answer 6. So yeah, let's check it. So yeah, it's fine. Let's run over the submit it. Obviously it would give the time limit exceeded. Ignore this. I guess this is their problem. Okay, so time limit exceeded. So how to optimize it? So what is the time complexity? Obviously you can guess, it is big of any square. It is big of any square. Okay, and space complexity is big of 1. Space complexity is big of 1. So how to further optimize it? If the interviewer asks you to optimize, how to further optimize it? One thing, that what was we were doing wrong. We were just for checking whether I is present or not, we were running another loop in the array to check. Suppose we have already pre-computed whether the that element is present in the array or not. Can't we just answer whether this element is present in the array or not in big of 1? So our time would be saved there. So we can do this using unordered map or unordered set. Okay, or even vector, because I know that I have to just store until uh, uh, a of n. So visited of, I would name this visited of n plus 1. Okay, now what I would do, just I is equals to 0, I less than n, I plus plus, I would say if arr of I, if arr of I is less than 0 or less than equals to 0, or arr of I is greater than n, then we would have to continue. Else what we will do, just we will store answer of I plus plus, means we have seen this element in the array. Now you can guess what I will do, just I will iterate through n I plus plus, means I am checking whether I is our answer or not. What do I mean by our answer is not? If it is not present in the array, then it will be our answer. So if before what we were doing, now we were just running another loop from for int I j is equals to 0 to n for finding the element. So now what we will do, if visited of, if visited of, okay, before that, if arr of I is less than equals to 0 or arr of I is greater than n, so we would have to pardon me. So just if we have to check if visited of I, if visited of I equals to 0, then it is our answer, then it is our answer. Okay, suppose again the same case as was in there, the answer was 6. So if we have encountered such a situation, so obviously our answer would be 6, means n plus 1, because there were no element from 1 to n which was not present in the array, so basically the our answer would be n plus 1. So yeah, this should pass because we are doing this in big of n time complexity. And let's submit it. It should pass. As you can see, it has been passed. So uh, if the interviewer don't like that you are using another array which is using big O of any space, then if he asks you to further optimize the space complexity, because obviously this time complexity cannot be optimized further, but the space complexity, if he asks to optimize, then how can you think of it? Again, you may notice here that what we were doing there, only we were just storing the elements which are less than equals to n. We are only interested in the elements which were less than equals to n. So why not only use the array itself? What I mean that we obviously we have been given an array of size n. Okay, so what I mean is that uh, I need 1, 2, 3, 4, 5 to be stored here. So what I mean, the zero index will store element 1. If it is present, then I will bring the element 1 at index 0. If the element 2 is present, then I will somehow bring the element 2 here. And if it is 3, then I will somehow bring here 3. And if it is 4, I will somehow bring here 4. And if it is 5, I will bring how some here 5. So if I am able to do this, then obviously our answer can be solved. So how can we do this? Now I am resetting this. So let's consider this. Suppose you have been given an array. I am not considering this case because all the elements are obviously in its correct position from the beginning. So suppose if the input is like this, 4, 5, 2, 3, and 1. Okay. Now 1 should be here, 1 should be here, 1 should be here, and 2 should be here, 3 should be here. So what I will do, just listen me carefully. Here it is index 0. So I can say that whatever, since now I will just bring the 4 to its correct position. I want to bring this 4 to its correct position. So what is its correct position? It is index 3. Remember, it is 0 based indexing, so it is AR of I minus 1. ARR of I minus 1. Its correct position it would be ARR of I minus 1. Okay. So I don't care about anything. I will just swap it. I will just swap it. So now it will become like 3. Now it will become 3, 5, 2, and 4. Okay. So 4 has reached to its correct position. Now what I will do, I can say that 3 is also it's not in correct position because here it should be 1. So I will why not I bring just 3 in its correct position. So uh, it is at index 2. Okay. So I will just swap without caring about what the element was there in. Okay, so I will bring 2 here and 3 here. Let's take another color. Okay, so it should be 2 here and 3 here. Now again we can check 2 is not 1, means 2 is again not in its correct position. So I will swap with at index 1 because I have already said ARR of I minus 1 we would have to swap with. So now uh, so now it would be, now it would be 2 here, now it would be 2 here, now it would be 2 here, and 5 will be here. Okay, so again the 5 it is not its correct position. So finally when we swap, the 1 would be here and 5 would be here. You can see here the 5 would be here and 1 would be here, and obviously we have already placed 2 at its correct position, 3 at its correct position, and 4 at its correct position. So we have got this array, we have got array like this. Now can't we check whether which element is not present in the array? So we will do this for all the elements which are greater than equals to 1 and less than equals to n. And if it is less than equals to 0 or greater than n, then we don't care where it will go after the rearrangement. Okay, so our goal is to make array like this, and you can observe here is that the number of swapping will not be greater than n. Why? Asymptotically it would be not be greater than n. In total it would be less than equals to n. You have already observed here that after performing to bring an element to its correct position, all the other elements will all also be placed in its correct positions. That's why it would not be greater than n. So we can say that it is big O of n. Big O of n plus it is n for traversing the array and n for swapping. So it would remain big O of n. It would remain big O of n solution. Okay. So I have explained it enough. So let's code it. It will be clear now. So if ARR of I is less than 0, less than equals to 0, or ARR of I equals to I plus 1, I will just continue. Why ARR of I is equals to I plus 1? Because it is in correct position. Suppose at index 0 the element 1 is present, so we have to continue because 1 is it in its correct position. Okay, and also if ARR of I is greater than n, so we would have to just continue. Now if that's not the case, then we would have to perform the operation of swapping. And also one edge case is here that suppose the same element, although it's less than equals to 1, is present. Okay, suppose it is here 1 also. Now 1 at its correct position. Okay, we will just move on to the next index. Now here it should be 2, here it should be 2. So what will we do? Here it should be 2. So we will again place uh, let me so yeah, so it is 1 and its correct position should be 0. Okay, so we will swap. What were we doing? We will swap it with 1. Again it remains 1, again it remains 1, again we will swap. So you can see that it will end up in a loop, so it will return your time runtime error. So we would have to also consider this problem. if ARR of I minus 1 is equals to uh, I plus 1, so we would have to, if ARR of I minus 1 is equals to ARR of I, then we would have to continue, because the element will remain same. It doesn't matter how many times you are swapping it. So okay, let's code it. While ARR of I is not is equals to I plus 1, until it's not in its correct position, we would have to swap it. And ARR of I is not less than equals to 0, and ARR of I uh, is not is less than n, sorry, it should be greater than 0, and then only we have to perform this. Okay, now we would perform the internal check, means if it is the same element with which we are at swapping with. Suppose I have just explained the case here. If it is 1 1, then I am talking about that case only. If ARR of I minus 1, okay, is not is equals to ARR of I, then only we would swap ARR of I comma ARR of I minus 1 comma ARR of I. If you just dry run over this case or take some input, then you will surely understand. Okay, else if this is the case, then we would have to break this loop, because we can't place the element at its correct position. So I have just explained the case here, 1 and 1. It is its correct position, so we will just move to the next index. And but ARR of I, ARR of I minus 1. What is it? ARR of I minus 1, ARR of 0. And with we can see ARR of 0 is equals to ARR of I. Okay, ARR of I is 1. So that's why we can't place at its correct position. Okay, if ARR of now if ARR of I is not is equals to, even after performing all this operation, we are not able to place the element in its correct position, so we have to return I plus 1, because that element will be the positive integer which is not present. Okay, so if after all this we would have to return n plus 1 for this case, if all the elements from 1 to n are present, then we would have to return n plus 1. So yeah, that's all about the. There is no need of it explicitly checking, because we are already checking here. Okay, so let's summary. Oh, sorry, it was 0 and your code output is 2. if error of I is not is equals to I plus 1, if error of I minus 1 is not is equals to error of I, then we would have to swap error of I minus 1 comma error of I. Okay, that's all correct. If still error of I is not equals to I plus 1, then we would have to return I plus 1. uh, I should just I plus plus. If error of I is not equals to I plus 1, then return I plus 1. If I do this like this, then let's see what is accepted. So yeah, it was accepted. So let's see why it was not getting accepted if we are checking here only. The case where it got failed is it was 1 and 0. Okay, so it is obviously 0. We would continue, so array would remain the same. Oh, so it would not strike a situation like this, because when the error of I is less than equals to 0, we were just continuing the answer. So that's why uh, at finally it will return n plus 1. What I am telling that when it will reach when it is at 0 index, it will just continue because error of I is less than equals to 0, and we are even not also checking explicitly which element is not present. That's why its answer should be 1, but it will return 2. Its answer should be 1, but it will return 2 because we were not checking this part. We were not checking. We were just directly returning n plus 1, which is 2 here. So that's why it was wrong. So what is the time complexity? I have already told you that it would be big O of and how I have already proved. Because this loop might seems you that we are running another loop, but if you think of it, you can uh, derive that it will not run greater more than n times. So it would be big O of n plus n. Why it is n plus 1? N plus n because n for running the loop and n for this loop. In total, it will run for n times. So it would remain big O of n. And space complexity is obviously big O of 1 because we are not using any extra space. So that's all about this problem.